So I think people who know logic a little bit will know that if you drop weakening from a logic, you get a relevant logic. So I wrote down a few titles related to that, but of course they were too close to honours titles. We'd already stolen it this semester. The word relevance, so it's just a very boring title. It's additives, but without weakening. Now what is weakening? Can everyone remember what weakening is? Basically, when you have a sequence, so it's a sequence of formulas. Yes. So this represents the potentially formula here. If I can establish it, the formula without this disjunction, then if I can establish the truth of this, so it's a proof of this, without the disjunction, I can read it to make extra formula to this. So something very simple. Probably you would expect in classical logic or intuitionistic logic. But it's also something you don't have in linear logic. So you drop linear logic beginning, that's one rule. What else would you drop in linear logic? Contraction, yeah. So contraction is basically making copies of A. So something like A kicking around, then I can make more copies of A. And I can use multiple copies of A going forward. And so it's well known that if you start to play with these two structural rules inside logic, you get lots of new logics emerging. Of course, dropping both, you get linear logic. Okay, these are the multiplicatives. So A and A is not the same as A, linear logic. But you have like basic properties like commutativity and so on. So A and B is equal to B and A. Basic properties like this, but you're losing a lot of the structured logic in this process. What happens is, in fact, when you look at the linear logic setting, you get two different additive operators emerging. Sorry, two different types of conjunction and disjunction emerging, which is the multiplicative and the additive forms. Don't want to go over them too much because we've already had a talk a few weeks ago by Bob where he introduced the additives. So this is not entirely one-on-one because we have we're going to go one step beyond what Bob has already mentioned. Okay. So let's start off with the system. I'm going to go straight into the system. So how are we going to define the system? So we use the system of deep inference. Okay, so deep inference is basically the idea that you take a formula and you apply a rule anywhere inside the formula. So you can apply it at any depth inside any context. And that's different from the sequent calculus. If you look at the sequent calculus here, I'm applying a rule at the topmost level, which is at the sequent level. So the sequent is this meta structure, and I can apply contraction here. But in deep inference, you would be able to apply contraction anywhere to any depth inside the formula. Okay. And multiplicative linear logic, this is just the basic multiplicative operators of a very specific form. So there's this rule here. So this is the multiplicative disjunction. It says basically it's saying A or not A is a tautology, which is something which you'd expect in most logics. another way to read it is if you see it as negation or this negation or is basically an encoding of implication, isn't it? You can see it as A implies A. Yes. Because how do you write out an implication? It's not A or B. Yes, that'd be A implies B. Okay. So A implies A, that's a very reasonable thing to assume. But we give it in atomic form, which Bob mentioned earlier. You can break down these axioms, A implies A, just like A implies A, where A and A are just atomic propositions. Okay, as a feature of many facti. So you can do this also inside the sequent calculus, by the way. That's special to deep inference. But when you do it the other way around, you can do this also for cut. As Bob mentioned, you can take the dual rule where you have basically the dual formula at the top, which would be A and not A, yes, if you dualize the formula. And at the bottom you have the unit, okay, and that is basically an atomic cut, which you can use to basically, which is going to be the elimination of A and not A inside the formula. So, we've got hand gestures. So what's a cut rule? So we have A, not A, delta. A, because we have A here, and not A here, we can cut along them and we can get rid of these formula. Okay, that's a cut rule. And of course, in deep inference, what you can do is, well, you say, well, this is actually an operator. This is basically a conjunction. You can bring these together, and then you can eliminate them, and further, you can break them down to this atomic form. Okay, so there's a symmetry you have in deep inference you don't have in the sequent calculus. Okay, and this operator, this rule over here, the switch rule, is all you need to capture the properties of the multiplicative operators, apart from, of course, the fact that they're associative commutative operators with the unit. Here we have a shared unit, so this means we're, for people who know linear logic well, this is in the mix form of multiplicative linear logic. Okay. So that's more of a recap than anything, because we've seen this before. I think we've seen it twice because, of course, this time last year we gave a talk which followed the talk we talked weeks ago. Yes.
So did you say the context of disjunctive here?
So my hearing is not perfect.
Did you say the contexts are disjunctive here? So I would usually think of a context as here's a bunch of things that are all true that we have this hypothesis.
Yes, because this is the right hand side of the sequence.
Oh,
there's no left hand side, so it's disjunctions on the right, conjunctions on the left.
Okay, yes.
That's the usual way to do it.
Do you, are there also standard rules for transfer like standard introduction rules, or are they advised by this?
Are there some additional rules on top of this for multiplicative linear logic?
It's really just these two rules and nothing else.
Yes, yeah.
That generates all the multiplicative linear logic.
Yes, and what's very neat about it is also, you notice the S rule, the switch rule, is self-dual. So if you swap the top and the bottom, then you do the linear negation, you get the same rule back, which means that the rule, if I take a system and I add just the inverse of this atomic interaction rule, this atomic cut rule, then you've got the multiplicative linear logic with cut. So it's really succinct, this system. And I think this has been known to category theorists for a long, long time. It's a kind of linearly distributive category.
Linear pocket.
Yeah. So this is basically category theory for people who don't know category theory. So it's basically everything comes out this term united. Yes.
Next question, but what's stopping the tensor on par from collapsing into one connector? Shared unit and
Stopping the collapse. You cannot prove that one implies the other. don't think that's answering your question.
Like the switch will have like a clear direction, right? Like you can't go the other way. So the switch is indifferent.
If we go from one way or one way or
You think you might be able to invert it by dualizing?
yes. Yeah. I think basically the tensor kind of is forcing you to split, or the times operator is forcing you to split the context into two things that can't interact, and you're never going to be able to get them back together. Yes, that's kind of.
You can link the C with one of the two choices of A and B, but once you link it to one of the two, you can't then take it back out.
Okay, and then this is again still a recap for Bob stock. If you want to add the additives to the system, you can do so in a very uninteresting, obvious way. So I'm not looking even at something as advanced as Bob was looking at. He looked at BP with the additives, where we needed like a few tricks. Like they're easy once you see the tricks, but you do need a trick. Here you don't even need a trick. It's really quite tricky. Okay. So basically, it's kind of obvious if you know the rules for the additives. So basically, what we have in the secret calculus, we have A with B, okay, along with something else. Then what I can do is I can try to prove this, and I can try to prove this. Establish this. Okay. And see, there's some reuse of this formula. This is the resource sensitivity coming in. Somehow this is more like a superposition of two things that I need to prove using the same resources. Whereas if I give you the multiplicative form, then you would need to share out the resources in order to establish a fact. So they're quite different from both the multiplicatives and additives are quite different from classical logic. Okay. And you can see the essence of this pattern inside this rule. Yes? If you show this to someone who does deep inference, they'll say, that's just a stupid way to do it. It's so easy. I mean, it's not really easy ways it works. Okay? Almost like direct translation of the rule. And similarly for disjunction, if we have something like this, so this is A or B, additively, what I can do if I want to establish this is I can we'll just try and prove one part of it, or I can do the other side. Yes. And you can see that that's coming through. So it's of course, if I apply it to the type of suitable context, I can have this, and they get this standard secret calculus for the additives. Now, and I don't have any slides for this, for what I'm about to say here, so I'm just going to talk. So that was nice. I mean, this was kind of obvious. What was less obvious, as I said, is how you then take this system and add the non-commutative operator, which is this calculus BP that we saw a few weeks ago. I don't want to talk about that. To talk about another dimension. And that dimension, I observed when I was trying to add not the additives, but to add nominal quantifiers to deep inference. Okay, this was motivated by problems in the pi calculus, where you can basically manage fresh names in a kind of primitive logical way inside of an embedding of processes with like fresh names being created and passed around and so on as pi calculus into logic. And all the fun doing that, I'm not sure what results I got out of that. It's produced lots and lots of pages of proofs. But one of the observations was that we know nominal logic for a long time. And in the classical intuitionistic setting, basically you have one nominal quantifier, which is self-G. Everyone agrees with that. Does everyone know that fact? Yes. So there is a nominal quantifier. It sits between universal quantification and existential quantification, and it's self-dual, and it says either there exists a fresh name or for all fresh names, and those two things are equivalent. Okay? They're De Morgan dual. It's De Morgan. It's if you apply the De Morgan dual, you get the set back. Okay? But in linear logic, strangely, these two operators decompose, and we end up with a pair of operators. And those two operators actually behave surprisingly much more like the PAC calculus does in terms of semantics. So we're not talking about syntax there, we're talking about semantics. That's maybe a subtle point, which is, again, I don't want to get too much into. I don't want to get too sidetracked. So we found that we have the existential quantification at the top, universal quantification at the top, nominals usually right in the middle, being self-dual. We found that in the linear logic setting, we found these two other operators in between. And basically, with nominal quantifiers, it's effectively you're dropping the ability to instantiate the variable. So you have, if there exists X something, then I could plug in the term T. I could plug in 3 or 4 or whatever. I could plug in actually a value for X, and then I can try and prove it for X. That would be a proof if it worked out with a value. You agree with that? Yes. And that plug-in in the value, basically taking something like there exists X, and replacing with the expression with the term inserted, is very much like weakening. So this is essentially weakening. Yes. So basically, you're taking the term and you're taking a smaller part of it. You're narrowing down the choices we make to that particular choice of term. Yes. And you're doing something very similar with the additives here. You have a choice here. You're narrowing down the choices there. So that's the important thing about the nominal quantifiers, is that you're dropping that ability because essentially you have a name and it's just a name, it can't really narrow down. Okay? And what's quite intriguing is you can do something quite similar with the additives. So what's happening in here? Maybe it's not so obvious here, but there's some kind of contraction going on inside this room. Can you see the contraction? Basically, you're kind of creating two copies of everything here, distributing it over. Yes? It's a contraction in there. We do have a contraction here, we have a kind of weakening here, built inside the additives. And what happens if we control them? So we get a new system. So at the top, we have still multiple linear logic, doesn't change. And now I've got a bunch of operators here. And what I'm trying to do.
Did you actually just have one slide? It's just going to get more and more packed.
Yes, I still have a mission to do a talk which has only one slide. This would be a real achievement. I have seen it. I saw an investment banker give a talk like that. Just went through one slide for like an hour. It was impressive. It was impressive. No, not quite that yet. Yes, so here we have, here is quite a different system. So we've dropped, what have we dropped? Important things we dropped. So we've dropped this rule here and this rule here. So we're not allowed to make choices. Okay, but we still want to have the kind of essence of how the additives behaved. And the essential thing was really this contraction. So that allowed us to do this. So we still want that A and A is equal to A, where A and A are the same. Okay, that's a property that we would like to have. And to do that, we can introduce a rule which basically says if I have A, then I can make 2 copies of it over the disjunctive. It's enough to have the disjunctive form, and also for it's enough to have just for units. Okay, and I make it inequality for various reasons. So we still want to have this idea that A and A is equal to A, and A or A is equal to A. So we have this contraction, this idempotency. But we want to get rid of the idea of weakening, so we want to get rid of this ability to kind of throw away bits of the formula. And I'm going to skip ahead to say, like, well, why would you want to do that, and why on earth would you want to do that in the first place? Well, I said, okay, it was a nice observation, and then just stayed as a nice observation for a while. And then I sat in a talk with people talking about probability distributions inside processes, and I was like, wait a minute. That's the same properties that these operators exhibit. So depending on time, we might be able to do that. So there does seem to be a motivation. If I consider this to be the combination of two probability distributions, if I basically say I want half of this distribution and half of this distribution to be weighted amongst each other, and I put them together, then I get the same distribution back. Yes? But no, okay, if I consider this to be combining probability distribution, say this was a half of A and half of B, half of the distribution, yeah, then there would be no relation between this and this distribution which concerns only A, unless B had some proper relationship to A which allowed it to collapse. A and B are the same. Yes? So, okay, maybe it's worth having a look at the system and see what it's like then. Okay. What else do we have here? Well, there's some rules which we need, which are unavoidable. So the first one we can see here, this one D, and don't ask me what D means, I've forgotten completely. But this is a rule that you will see for relating basically every kind of operator. I think there's something to do with functorality. We describe this way, but basically, if you take width and plus, these are kind of due to each other, this is and an or, yeah. If I write this, if I put, let's say, not A, not B, A, B here, you would get an implication, would you? This would be internalizing an implication, so it would be A and B implies A and B. Yes? So you're kind of internalizing the implication inside the logic, okay? That was a derived property in the previous system.
Yeah, it also looks, if you go back one side, look at the E rule, it looks like a version of that rule where, so there you had like one thing distributing over your disjunction,
Yeah.
which got copied into like both disjunctions. But here is split it into two different parts, which have to sort of be tracked where they're going. It's like the B, it's like the B plus D is distributing.
Yeah.
You're tracking which direction it goes.
Yes, there's a distribution going on.
Yeah.
These are kind of distributive properties that you kind of need to retain to get that combination to work.
Yes.
Having dropped the weakening and retained contraction, you still need some additional properties for that combination to work. Okay, these are the properties, and they all have the same form. Look, this is A B C D, A C B D. You just swap the middle ones, yeah, every single time. They have a clear pattern. And this is a known pattern within deep inference. Okay, that a lot of rules can be broken down into like basically this exact form where you're distributing one operator over another in this kind of way. So all of them are in this form. This one's quite interesting because it's self-dual, a bit in switch. So we have the additive conjunction, additive disjunction, and the distribution over each other. So swapping things around and just swapping B and C in the middle. Okay. This one might be a little bit strange at first. But actually, it's something quite common in deep inference again, and I need to give a bit of background there. So what operators is going on? So we've got plus here, and R here. Yeah, let's give an example which involves this rule. So I can say A R. Okay. One way, what I could do is I could apply the contraction rule to it, couldn't I? C down, and I can get A B or A. Very good. So all done this applied. Now, with this M1 rule, presumably there was a 1.M2. There was actually to be redundant or required in a larger system, and we just give you a minimal system. And I'm vague about things because this was about 10 years ago. So I don't remember what I thought this stuff. So, but here, what I can do instead is I can do atomic contraction. So I can do it basically to each of the atoms individually. Okay. And then I can apply this rule to distribute everything over each other. So I swap these two over to the again. So I get B coming over here, A going over there. These stay the same. Now the operators swap around. So this, yeah, and this ends up here. Oh look, I've got the same thing but now I'm applying contraction only to the atoms. And there's something nice about that, is that when you can apply contraction only to the atoms, it's atomic contraction, you can apply a whole bunch of fascinating proof techniques, basically decomposition. So you get a big proof, you look at all the atomic contractions, you just see where they're going to whiz around in the system if you move them around, until they're all at the bottom and all at the top. And then you can just normalize a bit in the middle, which is completely linear. Notice these are linear in the sense that the resources are the same at the top. Except this one. So you can isolate all the non-linear into one loop, and then push them out of the way, and then you have this thing in the middle where basically everything just goes through. And that's no technique. You can even do it in classical logic, you can do it in basically every logic under the sun, except this one. Okay, so even though I've given you that positive example, it will not work. This technique, this atomic contraction, will not be possible by these times here instead. That's surprising. So it's a first instance of a logic where this atomic contraction technique doesn't work. And that's why proof theory starts to become interesting, I think. Okay. So how does proof theory work? So what you do, basically, proof technique. So you have a derivation. This is deep inference notation. So C is a conclusion, at the top is premise P. So I can apply a whole bunch of rewrites of these rules, applied in any context, from the system null, which is the one which I've just given. And what I can do is do something, what I want to do is something like I described just a minute ago, is I want to take all of these things which are non-linear, there's only one non-linear rule, I want to just push it all the way so all the contractions are at the bottom. And then the thing is that when you contract through a cut, you create a contraction going up, an upwards contraction. It's the dual of that rule. Okay, which is basically what's the dual of that rule like? So it's like that. Yeah. And then they whiz up. And then they hit an axiom, one of these, and then they come whizzing back down again. So you get these things whizzing up, whizzing down, whizzing up, whizzing down. How do you know that's going to stop? Through the system. But if it did stop, it would be nice, because what would happen is at the bottom you have a bunch of contractions. Here you have something where you don't have to eliminate the cut. And if this is a proof, this will be the unit, which means that these are kind of redundant rules at the top. So you get something redundant, something which you can normalize, and then something trivial to do. Okay? And you basically, you can establish path elimination easily once you have things in this form. Problem is, cycles can occur. So if I do this in a naive way, if I grab these non-linear rules and I start pushing them through the system, then strange things can happen. This plot is wrong, isn't it?
It's 45 minutes.
Says it's 5 o'clock. Right. So hopefully I'll have time to explain. So what we have here is a contraction rule here inside a derivation inside. This is not a proof because the premise is A and not A. And the conclusion is, well, this is not the conclusion because it's been used on. The conclusion is this thing, so it's not A and A. This is a multiple conjunction, this is multiple conjunction, this is multiple conjunction. So basically it's like a big arrow, yes, from here to here actually. Okay, but it has structure. So it's the arrow has a structure which is the proof itself. Okay. And if I were to just randomly pick a contraction to do this trick where I push things through the system and up and down and so on, and I take this one and I end up with a problem. And what is, when I pass through here, if I follow this path, I'm going to duplicate it, so there's going to be a duplication here. When I follow here, there's going to be a duplication here, there'll be a duplication here, so you're going to get, basically, it falls through the system, just creating copies, so it becomes wider at the top, that's okay. Until it hits this point. Now, what happens at this point? Well, I'm going to apply a rule, which I think I've actually done yet in this slide, so this one. So this one here, when it hits, when the contraction hits cut, what will happen is it will pass through the cut and come up as a co-contraction. Okay? And there's something of trivial keeping at the bottom because at the end like it almost like a contraction coming down into units. Okay? So what will happen is the co-contraction will come up here, it'll flow up here, flow up here, flow up here, flow up here, and then it'll hit an axiom, basically is what this is. And what happens? Well, the dual thing happens, it's come down here, or it's come back to the south. So there's a potential that formulas can just get bigger and bigger and bigger if you choose their own contraction. They just go fly around the system, and then they generate bigger and bigger and bigger formulas at different terms. And as I said, if you could make contractions atomic like this everywhere, then there's a way of coping with that. But the thing is, we can't. Okay. So we need to basically do a lot more normalization than normal in order to get this working. And so what we do. So this one is described already. And what's happening here? So we have, for example, here. We have a contraction over a plus, and then we have a rule in which the plus here is active. Is that a typo? That should be. Let's see that there's a typo there. No, there's no type of what's happened here. C and B is swap over. Yeah. A and B are the same. Guess what has gone here? This has gone here. And this has gone here. So it's one of the distributive tables. The problem is that you haven't seen it before. This is not rich. Okay? So it's one of the dual rules, of course. There can be dual rules in the system when you start to put cutting in the system. And what happens here? Well, notice that the contraction going down, it starts to go up again. So as soon as it hits this rule, it changes direction, and it starts flying up the system as a full contraction. It's roughly of the same size, yes, although actually C and E might be completely unrelated to it, so we can't really say much about the size going down. The formula, the proof is got bigger, it's got fatter, hasn't it? And we've got two instances of this rule which might, and notice that these rules cause explosions, which means that this can cause an explosion, and this can cause an explosion. Which means that any contraction which might later on come into both of these is going to be affected potentially by that law in the proof at that particular point. Yes? So it's not obvious in the terminates at all. What's happening here? Almost the same thing. It's just a collision with. It's a collision on the other side. It's a symmetric version, isn't it? What's happening here? Almost the same thing. What's happening here? Almost the same thing. Oh, we're getting a pattern. So maybe actually it's not so bad. We're seeing all the cases, but there's a similar pattern. There's a variety of cases. The contractions coming down. It's hitting associativity this time, and it's creating two copies of associativity. A co-contraction going up. What about these rules? So here, what's happened? Well, we have again this down. We have what's happened here?
Yes.
So this is a different rule, isn't it?
Yes.
Right, because this, the other one was up.
Yeah. This is a down rule. This is the opposite one, which we looked at the other before. This is a down rule. And when the down rule is hit, you can see different things happening. The two copies of the contraction that are smaller being created either side of the operator which has been contracted. So there is an A and B, A or B being contracted, and you can see that the A and B have now split off the other side of the down rule. And that should be a pattern again going through with the down rules. Yes, the down rule, somehow this is behaving like a down rule, even though it's self-dual. Associativity can also be treated like a down rule. That's interesting because there's a choice there, isn't there? You saw associativity earlier. It can behave like an up as well. So associativity is good. That's the one thing with the difference. What else do we have? Yeah, it's a contraction, it's a co-contraction. There's a bit of an explosion that goes on, and that explosion can be managed in many different ways, so you just need to make a choice what you're going to do. And let's do it this way and see whether this internally writing system works out. What's happening here? Traction is going inside a co-contraction and going up. Yes, so the co-contraction member is combining things at the side of the width. That's happening here. Yes, and then the co-contraction is happening inside. What we do is we can just push the co-contraction down inside the contraction down inside the co-contraction. Okay? And what's happening here? Yeah. So they pass over each other. So basically that you can see the direction flow is being contained. Co-contraction is going up, contraction is going down. Whoa! Yes, it's a great flight. Now, question is, does this terminate? As I say, if this terminates, then we're sorted. Like the proof technique that I mentioned at the beginning, that strategy is well known and it's easy to handle. It's just like becomes like kind of following through with the things. But does this terminate? What is the measure that you put in it? And essentially, you're going to have to give a rank for every single contraction and co-contraction system. You're going to have to have an algorithm which is going to avoid this situation. And it's actually quite easy to do. What you do is you just pick bottomless contraction, read that down until there are no co-contractions. Everything's turned into a co-contraction. Then you do the same again. With the co-contractions, you can read them all up, which might create more contractions. Keep them going, and that process will eventually terminate. Okay, and you avoid cycles where you end up just getting things getting larger and larger. But larger doesn't mean like size of the proof in terms of like at all, because the proof is going to get large. It's going to get exponentially huge or hyper exponentially huge. Yes.
So you alternate between contractions all the way down to co-contractions?
Yes, that's because you can basically you can eliminate all of the contractions by pushing them all down until they become they're either at the bottom, in which case they're harmless, they're already deformed to be, or they've turned into co-contractions. And then you can start them again. And you're better off continuing to proceed. But proving that's actually going to work, you need to come up with a right levels of contraction. Basically, how long is that process going to go on for? How many things is it going to collide with? Out of those collisions, how much more problems are you going to create for everyone else? Okay? And just writing that down takes a huge amount of energy. Okay, I can write it down informally, write it down formally. That's another story. Okay? And then this is where we go back to Bob's talk. See. So even for this simple system at the beginning, okay, it takes a bit of work to do it in independence. You have to consider a lot of permutations. Also, you could do it by constructing some kind of choose space and with the right properties, and then doing 3 or 4 little checks, and it all went through. It's kind of like magic. And what's nice about this is there's a lot of these kind of like operators distributed over each other, which is essentially what Bob was exploiting inside the systems. It's permutations. So my research question here is, can we save all the effort of coming up with proving that thing terminates, and instead come up with just castings inside choose space of some sort, and come up with a result more efficiently and more cleanly. Because formally proving things with this number of permutations, this number of rules, this generates a lot of cases to check, is very error prone. Whereas Bob's approach was able to act that. So I think you would agree that you would just not really want to even set out improving the direct result and like that with all the permutations, and it would just be you'd be there forever like checking cases.
I think you'd spend a lot of time defining the measure and including a lot of just facts that you would need more than write down it would take years to
Yes.
just come up with all the little language you need about.
Just knowing that you've done the exhaustive case analysis.
Yeah.
Yeah. That's straight.
I mean, again, it would at least present you with all the cases. Whether that's easy.
It's the best of the pen and paper where you just miss one and then.
Yes.
Yes.
Although I do wonder if there could be some hope for a reverse engineering approach where you do the semantic proof, but then somehow manage to extract from it the correct rank measure.
Yes.
Yeah.
Yeah.
At the same time, it would be fascinating if it didn't work because of that. Because essentially, you have to do the same work in the end anyway, because somehow that rank is really fundamental.
But yeah, so it depends on exactly how algorithmic the rank generation can become once you understand the underlying structure.
Because where the measures went was kind of mysterious, wasn't it? So
Yeah.
it's just
I mean, in some sense,
this
it's
new
like
magic.
relying on determination. Some strong, some normalization proof, right? That you're relying on.
So this is why I'm digging up these old slides again, because like this got me thinking, can we do this better? How am I doing for time? So I don't have that clock. This is wrong.
It's not 10 to.
And okay, well in that case, I'll just quickly zoom through the actual slides, which is now where did this come from? This whole concept. Well, okay, so we like coffee, of course. And there's a famous problem where basically you design a coffee machine, you put a coin in, and you get to choose whether you want tea or coffee. Okay, a few people still like tea. Maybe it's time of day. It's later on in the day you have to drink tea because you've drunk too much coffee. Okay. And then there's another machine where you put in a coin, you get the tea, but the machine is chosen for you, whether you get tea or coffee. Okay. And then there's yet another coffee machine, which basically, so it's basically, there's an actor inside that will actually choose, okay? And then there's another machine which will, with probability 1/2, give you tea or coffee when you put the coin in. So these are 3 different machines, yes? And we can actually start to represent these inside this kind of system. So now I have bumping up with mathematic, the non-commutative operator, which is this operator here, which is I do A, and then I choose between B and C. Okay? And here I have that I choose between putting in A, this coin, and getting tea, or getting coffee. And there's an implication between these, like these linear logic. So there's implication, and that corresponds to a well-known property, which is simulation. Basically, this machine where I actually get to choose afterwards can simulate anything that this machine can do. Remember, this machine didn't give you the choice. You put in the coin and you got your whatever the machine decided for you. Yes, this is not the other way around. And the neat thing is that implication is out with respect to this very classic process calculus construct. Don't really want to go too much into this because of the time. I want to get zoom onto the probabilistic stuff. Basically, this is the normalization technique which allows you to establish the fact that I've just stated, that implication is sound with respect to simulation. Okay. And that's kind of, it's probabilistic in a way because you can consider a probabilistic test. Basically, if you test one machine, which is tested, I put in the coin and then toss. So put in the coin and then toss the coin, choose tea or coffee. And in one machine, I will always win. I always get what I want, and the other machine I'll fail the test. The probability 1/2. So there's a probabilistic test with this. I kind of suggest that somehow linear logic is quite probabilistic in the first place, even before I've added these operators. But now what I can do is I can take the operator which I've just invented and I can give it a weight even. So it's okay, you can assign a weight to each of these operators. So you can have like values passing around. Here is like a probability distribution, it might be other kind of things you want to put in, like some kind of addition or whatever. You can actually do calculations for these operators. There's a whole world of possibilities there. But I can establish this fact that this machine simulates even the probability of that machine. Now, why is that the case? Well, because the machine tosses a coin with probability 1/2 gives you tea or coffee. What I just need to do to simulate it is wait to see whether this is tea or coffee, and I can then just choose the button, which corresponds to what the coin chose. Yes? So I can simulate it when I have the control of the choice. And this is a well-known result in probabilistic process calculi. Such a thing should simulate such a thing. Okay? Again, that's an implication inside the logic. So we can start to prove things inside the logic, and then this is how you do it in process calculi, and this is how you would do it inside the system which I've just shown you. Just build a proof. If you build a proof using these logical rules I've just given you, or you can do the process classic process calculus technique. You build up the relation and you check the relations for 2 things: one to do with the probability distributions, one to do with transitions. Yes.
How do we define the weight? When it's 1/2, how do we define it?
Where are the weights here? So initially there's no choice, that's why there's 1 here. So it's probability 1 that A will be chosen. Coin. Then I put in the coin. One side. The other side doesn't have a choice. Even probability 1/2, okay, it's going to behave like B, and the other with probability 1/2 is going to behave like C. And then I have to split those 2 probability distributions into the case where I just have the Dirac distribution, which is just like probability 1 is going to happen, probability 1 is going to happen. And then I need to kind of split the other side into 2 pieces. And in fact, that's easy to do because it's just the same complicated. I don't know if that answers your question. So it kind of gives you a feel in the 3 minutes I have remaining. Okay, so it's quite nice that it's early that some atoms sometimes sit between the additives. In fact, there are infinitely many of them because I can give a red one, I can give a blue one, I can give a probabilistic one, and so on, and none of them will apply each other. Unless I add further discrete properties, which kind of say like one is somehow the others, potentially is even like a whole lattice structure of these additives, which the contrast to these additives, they're unique. If I find the red and the blue conjunction, I ask about one applies to the other, given the same rules, then one will apply to the other, be logically, but these will not be logically. That's a phenomenon known, for instance, with exponentials. So they are not color. They're infinitely. Okay, I don't want to go on too much because I think that's